Hello, welcome everyone to the AstroBit podcast, brought to you by your home for curated space news, astrobitica.com. I'm your host, Alan, the Astro Writer, and this is our next episode of Astro Wife Asks. In this segment, my lovely wife, Raylene,
hi everybody,
asked me about an astrophysical, astronomical, or space-related subject she's curious about, and I do my best to explain it. It's a fun way to dive into the wonders of the cosmos while keeping things approachable and conversational. So, without further ado, Astro Wife, what are we going to discuss today?
Today I would like to talk a little bit about black holes. So primarily my first question is, what is it and how does it form?
All right, black holes. Some of the biggest things in the universe, definitely some of the most mysterious things in the universe. These are cosmological objects that we know a little bit about, but we don't know everything about them like we do on a lot of planets and stars and stuff. So a lot of mysteries to be held in black holes. So what they are, a black hole is essentially a point where gravity has collapsed into an infinitely small point in space, creating this giant bucket essentially in the space-time continuum. So imagine if you have a bed sheet and you pull the bed sheet tight, and then you put a super heavy object right in the middle of that bed sheet, right? It will pull the bed sheet down and create kind of this hole, kind of like this bucket. Now imagine that super heavy object just goes indefinitely and forever, continually to pull down into a point unknown. That is a black hole where gravity is so strong that nothing can escape from it, not even light. So we have this thing in astronomy called escape velocity, right? If you want to leave the Earth or you want to leave the moon, you have to travel at a certain speed to reach escape velocity, which means you are traveling faster than gravity can hold you down. And in larger planets, you have to go faster. In smaller bodies like the moons and asteroids, you don't have to go that fast to reach escape velocity. Well, in a black hole, the gravity is so strong that even if you were traveling at the speed of light, which is 186,000 miles per second, you could not travel fast enough to reach escape velocity of a black hole. And that's why we call it black, because no light can escape it.
So we were watching Star Trek, the first one, the other day. And you know how Spock with the red matter, and then was that a wormhole or a black hole?
Okay, so red matter is totally made up, right? That's science fiction.
Yeah, I know, but...
yeah, he was essentially creating like a micro black hole, right? To collapse whatever, I think it was the star, like a star was about to go nova and destroy a planet.
Yeah.
He was essentially creating, red matter, I guess, is a hyperdense object or material that it could create like a micro black hole or a tiny black hole to suck up the star before it exploded and destroyed the planet.
So I also know, like, we don't know what's at the bottom of a black hole or, like, what's at the end of it, obviously, because you can't get out and...
Yeah, exactly. We have a pretty good idea about how a lot of black holes form. Not all black holes are the same. There are different types of black holes. We have a pretty good idea about how they form, how they work on the outside, things like their event horizon and accretion disks and all this other stuff. But as far as like what's inside a black hole and how the laws of physics work down there, we're not really sure, right? Because we can't go down in there and come back out and study that. All we do know that, or we think that at the bottom of a black hole, like the laws of physics completely break down, time and space are meaningless. It is this point, that's what makes it super mysterious, because we don't really know what goes on down there, and our best explanation is it is unlike anywhere else in the universe.
So you mentioned an event horizon just now. What is that?
Okay, so an event horizon is like the point of no return in a black hole, right? So you can travel towards a black hole and turn around at certain points, right? Or you can escape. But there comes a point where you're like falling off the edge, essentially, where you get too close to its gravitational well that you cannot escape it anymore, and you just continue to fall inside the black hole. That is the event horizon. It is the point of no return, where you can't turn around and leave the black hole anymore. You've crossed that event horizon. You've crossed the point of no return. You are going in that black hole, and there is no coming out of it at that point.
I mean, you also mentioned like black holes come in different shapes. Can you explain a little bit more about that?
Yeah, so we have observed really two types of black holes, right? Like stellar mass black holes and then what we call supermassive black holes.
Like the song?
Yeah, like the song. And theoretically, we think there's these things called primordial black holes and micro black holes. However, we have yet to detect those. So let's start at the very beginning. And by the beginning, I mean the beginning of everything, the Big Bang. Just after the Big Bang, there was a lot of material in the universe that was created in like fractions of a second. And in that moment, in that brief moment after the Big Bang, there might have been material dense enough collected in a single area where it collapsed into a very early black hole, literally happening seconds after the Big Bang, right? Even like milliseconds after the Big Bang. Those would have been primordial black holes. And then supermassive black holes, we think, also formed around this time as well. So, in the very early universe, well before there were lots of stars and planets yet, when there was just a lot of gas and material out there, we think that a lot of this material and gas kind of clumped together enough that it eventually got so gravitationally strong that it collapsed space-time into a supermassive black hole. And then as that black hole, because they essentially exist forever, basically, like for the most part. We'll talk about Hawking radiation here in a little bit. But it just moved through the universe. It collected other dust and material. It created these stellar nebulas where it created stars, and then stars exploded and created planets. And that's why we have supermassive black holes at the center of galaxies. So we think these huge supermassive black holes were created at the early part of the universe, and they've just had, billions and billions of years to collect stars and planets around them, and that's why they're at the center of galaxies. Now, the ones we know the most about are what we call stellar mass black holes. And these are black holes that were formed after a star went supernova and collapsed in on itself. So there are several different types of stars. We've talked about a few in different episodes, but the very, very large stars, and we're talking stars 20 to 30 times bigger than our star, when they get really late in their life and they have exhausted all their nuclear fuel, so they can't produce heat anymore, gravity starts to work on them and they collapse down, right? So they can't produce heat, which pushes against gravity. They've run out of their hydrogen, they've run out of helium and all that other, so they start to cool off. Gravity overcomes that stellar tug of war and collapses that star in on itself. And if what remains at the end after that supernova is big enough and dense enough, it will continue to collapse in on itself, creating a stellar mass black hole.
So a black hole has a lot of gravitational pull around it, correct? But um, if it's at the center of a galaxy, why doesn't it pull stuff into it?
Okay, so some do, and some don't. It kind of just depends on the local conditions there, right?
Like a vacuum cleaner.
Yeah. So that is the old misconception that like black holes are just like sucking up stars and material and stuff all the time. Some absolutely are, right? But it's not like you plug it in and it just starts sucking up material. So the material that is just before the event horizon at a black hole, the force of gravity is still strong enough to break it apart, right? So if you put like a planet or a star near the event horizon of a black hole, the gravitational forces are strong enough to rip apart that star and rip apart the planet into smaller materials, right? And then it will start to, because the way gravity works and we orbit, right? The material will start to orbit the black hole and go around and around and around.
So if it finds that like sweet spot, that Lagrange point.
Not a Lagrange point, but yeah, when it finds that sweet spot where it can orbit the black hole without falling in, because the gravitational forces are so strong, that orbit is really, really, really fast, right? So that material is orbiting the black hole really fast. As it's orbiting so fast, the material heats up and it glows. And that is what we call the accretion disk. And that accretion disk can glow so brightly that if you were looking at it from a distance, you would think it was a star. It would shine as bright as a star. And we call those quasars, right? Because in the early days of astronomy, when we didn't have super good telescopes yet, or we hadn't theorized about black holes, we looked at these bright points of light and we thought they were stars. Turns out they were just the accretion disks of certain black holes spinning, getting the material really hot and bright, so it was bright as a star. So we call those quasars, or I like to remember them as quasi-stars, right? So it's not really a star, but those are quasars.
So, can a black hole go from a primordial black hole? You said that was the little one. Can they go from a primordial black hole to a supernova black hole, or do they just stay the same size once a star collapses in on itself and becomes a black hole?
Well, primordial black hole just means it existed at the beginning of the universe, right? There is a thing theoretically called a micro black hole, and a micro black hole is a super, super tiny one. It's only existed in theory. Obviously because of its size, we've never seen one because they would be really, really small. A micro black hole would be like the size of a baseball. That's how small it would be. Obviously, that's going to be basically impossible to see unless we're standing right on top of it, right? So some black holes, as it accretes material into it, as material crosses that event horizon, it will grow and get larger, right? Because it's adding kind of mass to that already gravitationally massive object, or whatever it is. That's called the singularity. That point at the bottom of a black hole that is creating that gravitational mass is called the singularity. So as it accretes more material, the black hole may get bigger. Sometimes black holes merge together, like they bump into each other, just like you bump into your coworker when you're walking down the hallway. Black holes do that, especially like black holes at the center of galaxies. Galaxies collide with each other. So the supermassive black holes at the center of them sometimes collide and merge and make even larger black holes, right?
That's
And
somewhat terrifying.
yeah, that is. And it's really scary. If you look forward in the universe, and I mean trillions and trillions of years into the universe, essentially we become a black hole universe because all the material eventually gets or falls into a black hole at some point, and all the black holes start to merge with each other. And like I'm talking like trillions, hundreds of trillions of years in the future, even. The only thing that will be left are black holes.
So, can a black hole die?
Yeah, well, in a way, right? They can sort of dissolve in a way. And this is what Stephen Hawking did. This is what he was super famous for. He theorized this action called Hawking radiation. And we're getting kind of advanced here, so hang with me. All right, so Hawking radiation. Out in the universe all the time, these particles, antiparticles and regular particles, appear and disappear in the universe all the time, right? It's just the nature of our universe and how it works. These particle and antimatter particles just pop into existence. They collide into each other, and when matter and antimatter collide, they annihilate each other, equaling, kind of a 1 minus 1 equals 0 thing. And they dissipate immediately. Now, sometimes one of these pair of particles will just manifest in the universe right at the edge of a black hole. And the positively charged matter particle will be on the outside of the event horizon, and the antimatter particle will be on the inside of the event horizon. So if not even the speed of light can escape that event horizon, it's the same thing for a matter-antimatter particle because they don't travel faster than light. So what happens at a tiny, tiny little bit of that antimatter gets into the black hole and annihilates a tiny, tiny little bit of matter that was in that black hole, thus making that black hole just a fraction of a fraction of a fraction smaller than it was a millisecond ago. Well, if we take this concept and we extrapolate it out, again, over trillions and trillions and trillions of years of these particles popping into existence, the antimatter one getting sucked into the black hole and annihilating matter, and the positively charged matter molecule getting shot out into space, over time, that black hole will dissolve and get smaller and smaller and smaller and smaller until it dissolves and dissipates completely. Now, this is all theory. Obviously, we've never witnessed this. We've never observed it. We can never measure this just to the nature of black holes, but in theory, Hawking radiation, that's how it works, so that, some black holes will eventually dissolve.
Isn't that one of the reasons why Stephen Hawking never won a Nobel Prize was because they couldn't prove it?
Exactly. It's just theoretical. It could not be proven, right? Now, before we, question like theory here, like theory should obviously be investigated and questioned, right? But it's pretty sound theory, right? He was basically the smartest man in the world during his life, right? So this is not like he was just, sitting around making stuff up, right? The math is there. The math absolutely makes sense. But again, it's just something that currently we lack the capacity entirely to either recreate in a lab or measure out in the universe. And like I said, unless we were standing right on top of a black hole, at which point we got bigger things to worry about.
I just have one more question. What do you know what the most famous black hole is?
So probably the one right in the center of our galaxy, right? In the center of the Milky Way, there is a supermassive black hole called Sagittarius A star. That's its name, right? Because if we are looking at it from Earth, it is through the Sagittarius constellation, so we call it the Sagittarius A star. And that is the black hole at the center of our universe. We have taken a picture of it, essentially using microwaves. We didn't take a picture of the black hole so much as we used microwaves to take a picture of the accretion disk and the material orbiting around the black hole. But that, I would say, probably the most famous one because that's ours. That's kind of the reason why we're here. And the other thing about Sagittarius A star is it is feeding on material. It is collecting material around it. But fear not, it is a tiny, 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 tiny amount. There is no concern right now of Sagittarius A star going on like a massive binge and just eating up all the stars and planets in our galaxy. I once heard it equated that if you were to scale Sagittarius A star down to the size of a regular human being, it is accreting as much material as an average size human being if they were to eat 1 grain of rice every 10,000 years.
Oh, wow.
So that is the scale at which Sagittarius A star is, consuming material. Just a ridiculously small amount. There is no fear of it going out of control and consuming the galaxy anytime soon.
Going on a rampage. Yeah. Cool. Thank you. That was very interesting today. I've always wondered a little bit about black holes because they're, like you said, a mystery to everybody. Because we don't really know what's in them, where they go, and really what they do.
All right. Thanks so much for tuning into this episode of the Astrobit podcast and this latest episode of Astrowives Ask. I hope you enjoyed our conversation and maybe learned something new along the way. If you want to explore more curated space news, don't forget to check out astrobitica.com and follow us for updates on future episodes. Until next time, keep looking up and stay curious.
Bye.